right, so here is the Chapter 7 review. And we're going to talk just real briefly about what we did for Chapter 7. We talked about logarithmic and exponential functions. Okay, logarithmic and exponential. So in Chapter 6 we talked about polynomial, and now we're going to be talking about different types. And we started Chapter 7 by talking about exponential functions, I believe. So exponential functions are in the form of y equals some number a times some number b, which is referred to as the base of the exponential functions, to the power of x. So the big thing for exponential functions is x is in the exponent position, right? X is in the exponent position. So x is not, down here, like where we would see it normally in polynomial functions, with numbers in the exponent. No. We have numbers in the base position and the x in the exponent. So that's the big thing. The different bases yield us different shape graphs slightly. And so this is the general shape for an exponential function, as you know. It kind of grows really slowly to the left, and then passes through y equals 1, and then starts to take off, right? That's the general shape. Now, y equals 2 to the power of x would be shown here. Y equals 3 to the power of x would stay closer to the x-axis for longer, and then come up through y equals 1, and then it would increase a little faster. So that's what maybe y equals 3 to the power of x might look like in comparison. And we talked all about that in our lessons. Okay. So if you want a little bit more study on that, go back and look at the lesson. But you basically take any x values and you put them as the exponent on your base, and then that's what you get for your answers. Plot those and you get this exponential type graph. Okay, what happens if we have a base that is between 0 and 1? Well, if it's a fraction like this, then you have the same typical shape, but it's kind of reversed. It's flipped around the x-axis. So it starts really large and then drops quick, and then comes down through y equals 1, and then starts to get closer and closer to the x-axis, but actually never really touches the x-axis. It never touches the x-axis. It just gets extremely close to the axis down there. Okay? But that's generally what this looks like when you have a base that's between 0 and 1. And so it's summarized here. When we have a base greater than 1, then it's an increasing function. And we have a base between 0 and 1, it's decreasing under the general form. So domain is XER. You can have any x values. The range, though, is y greater than 0 for these. Okay? And that was our first look at an exponential function 7.1. 7.2, we talked about characteristics. We did this little paper folding exercise and how many layers we would get. If you fold the paper once, you get 2 layers. If you fold the paper twice, you get 4 layers, and so on. Okay? So we talked a little bit about end behavior as well. Okay, end behavior. All right. We did talk about what happens if a is negative. Okay, so with the basic exponential functions, exponential growth and exponential decay, where it decreases, usually the a is going to be greater than 0. But we tested out what happens when a was negative, and we found out that this exponential function flips about the x-axis. Remember that? So with a a value, it looks like this. But if you make that a value negative right here, if we were to do that, it does this, doesn't it? It flips it this way. Okay? So we tested that out as well, even though that's not a big focus here in this section, I don't think so. Okay? Now, the a value also gives us an indication of what the y-intercept is. That's very, very important. So if you have a equals 1, then y-intercept is 1 always. If you have a equals 4, y-intercept would be 4. It multiplies everything. Every value of y multiplies it by a. Okay? We talked about that as well. All right. So 7.3 we talked about. So here's where we sort of tested the a value being negative. And we also said if we have a negative base, that doesn't really work, right? Because the points bounce back and forth, and it is not continuous. So you will not see a function if the b is negative, so that's bad. Okay. All right, so then we turned to logarithmic functions. So log functions, you'll see on your calculator this log button right here, log. That's what we're talking about, logarithmic functions. And logarithmic functions, we found the graphs of those were a reflection of the exponential. So if we had y equals 10 to the power of x, where 10 was the base, it would be a reflection, the log of x base 10 would be a reflection about this y equals x line. And that's kind of, you get this opposite thing happening. And so logs are, we're looking for exponents for logs, right? So if we have 10 to the power of this exponent 4, we get 10,000. Well, if we returned that around into a log statement, the corresponding log statement would be log of 10,000 base 10 is what? Well, this is, we're looking for the exponent. So this is 4. The log of 10,000 base 10 is 4. The log of 32 base 2 is, well, we're saying 2 to the power of what gives us 32? That would be 5. Okay. The log of 8 base 2 is 2 to the power of what is 8? Shout it out if you're awake. Huh? Well, 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. So 3. Okay? Log of 8 base 2. What's log of 49 base 7? Are you guys sleeping or don't know this one? Don't know this one? 7, so, okay, here's the next thing. 7 to the power of what equals 49? That's what we're looking for, guys. 2. Yeah, 2. So we got 2 here, right? 7 to the power of what? Okay. You guys are looking at me very strangely now. You don't remember that? Okay, you need to look back at your notes, finish that homework, I guess. Okay, we also talked about a special base E, okay? We've got bases of 10 and 2 that we've looked at just now, but a special base E says this, that if we have log of x base E, that E base is special in calculus. We did not really go into too much why, but you do need to understand what this button on your calculator is, the ln button right here. That's the natural logarithm, and that is simply log of x base E. Very important. There was a question on your quiz, I think. There was a quiz. You had a quiz, and there's a question that I think pretty much everybody got wrong. What was it? Y equals ln of 72. Natural logarithm of 72. And the question was, write that in exponential form. So it makes sense now why you guys didn't get that one right. If you were really struggling with this one, I'm sorry to say. But yeah, this makes sense now. Okay, if you don't get this, so converting from exponential to log is very important. Remember, this is the base right here. Just like in an exponential, this is the base. Base, 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 base. This is exponent, just like this is exponent, okay? So you can fit all that together. So how do I rewrite this? Y equals ln, and that's my abbreviation. You'll hear me say ln, that means not natural logarithm. Ln of 72, well, this is, guys, log 72 base E, right? Okay? So the corresponding here, the exponential statement is E to the power of Y equals 72. Base to the power equals this. You just use those three numbers and you rearrange them. You just put them in different spots for the different equations, okay? So base to the power equals this. Base to the power of equals this right here. And if you're changing this, well, this is base, so log of E, okay? Log of 72 base E equals Y. You go backwards, okay? You might have to review that one, okay? So logarithmic functions look like this. They they kind of decrease down to negative infinity here. They go this way forever and never quite touch the x-axis, but get really, really super close. And they pass through x equals 1. So there's x-intercept for log functions, but no y-intercept. The opposite is true for exponential. There's a y-intercept, but no x-intercept. And then as this rises, it sort of starts to flatten out. It doesn't ever actually flatten out, but it starts to kind of look like it flattens out. But it still rises as time goes on. It still rises higher and higher. Okay. All right. Negative log flips around the x-axis here. Okay, positive log x, negative log x. Okay, and that was 7.4. And 7.5 was modeling data using exponential and logarithmic functions. I also saw a few of you got this one incorrect on the quiz too. When you're using your graphing calculator, guys, here to find this, okay, so we're going to do stat calculate, right, for the line regs and stuff like that. So if you go down, okay, a lot of you for logarithmic functions use this logistic function. The logistic function is not the log function. It's not the same. The reason why we learned about ln is because this is the log function, ln regression, logarithmic, natural logarithm regression, not logistic, okay? So you want to use this one, ln reg, for your natural logarithm, okay? Not logistic. Logistic is a different shaped graph altogether. If you take calculus with me, we'll talk about logistics functions. All right. Okay, so there's a summary there. This one, see? Y equals a plus b ln x. That's the format that you'll get your log function in when you do your calculator regression. All right. Was that it for exponential and log graphs? Oh, if you have to find the intersection between a graph, right? You do your second function calculate and you do intersect here. Now, I don't have any graphs listed. So let's say I have y equals 5 and I have y equals, let's say, x squared. Okay. And actually, I'm going to go to y equals, let's just do y equals 1.5. Okay, so if I graph those two, here's my graphs. If I want to find the intersection point, and let's say I want to find this right one, it's second function calculate, number 5, intersect. And it'll say, is this the first curve you want me to consider? Sure. Is this the second one? Yep. And where do you want me to guess? So now there's 2 here, isn't there? So you move your cursor over to a spot that's close to the one you wanted to guess, and you hit enter again, and it'll give you exactly x equals 1.2247 and y equals 1.5. So that's the point where they intersect. Okay? That's how you do that with a calculator. And that's that for chapter 7. I would encourage you to go to mrmathwell.com if you would like to watch any more videos in depth. And this review video I will put right here up on the website very shortly, so you can watch that. Any questions from you on chapter 7 at all? Yes.
How do you convert the equation from logarithmic to exponential?
Okay, how do you convert from logarithmic to exponential? Okay, how do you rewrite that? So back to that ln of 72 type question, like right here?
Yeah.
Okay, I can set up a couple of those for us, practice those. All right, so just some extra work on logs and exponential going back and forth. So here we go. Remember, this is the base of the log, so that's going to be the base of the exponential. This is the exponent. Remember, with logs, we're looking for exponents. So that's the exponent. That goes there. And then this is the sort of the object of what we're taking the log of. So that equals 49. You follow the lines here. It's base to the power of equals this. Base to the power of this equals this. Okay? Let's do this next one over here. Base, if there's no base shown, that's a base 10. So 10 to the power of y equals 13. Okay, that's the corresponding exponential. Let's go backwards now from exponential. So y equals 2x. Okay, well, x is the exponent, so that's what the log equals, right? What's the base? Well, 2 is the base, right? So 2 goes here as a base, and then this is y. Because 2 to the x equals y. Okay? And again, over here, whichever one you want to write first, I don't know. I mean, the exponent's what we're looking for. That's 5. Log, the base is 2, and then 32 goes the only available spot. So that's how you kind of go back and forth. Does that help?
Yeah.
Yeah, is that what you're looking for?
Yeah.
Okay,
Thank you.
you bet. Anybody else have any questions? All right, well, good luck studying for your test tomorrow.